Hi, we're Team Mars from Marquette University. I'm Matthew Braccio.
I'm Tim Campbell.
And I'm Dean Kamutsos.
Before we start our presentation, we have a few safety considerations. First off, we perform a routine inspection before we start up the robot. We also have one team member designated to press the emergency stop at any given time, and we maintain a 2-foot safety radius around the robot whenever it's powered on. Our safety features include an ISO-compliant emergency stop, high current fuses, and remote kill switches in the event the robot operates outside of its designated parameters.
So what this team set out to do is win the competition. No, we're not done. We know that's no easy feat for a first-year team, but we genuinely believe that's a possibility. We use certain historical analyses to help us really gauge the competition and what we were dealing with. We know that we have access to the raw historical data for previous years, particularly the last 2 years. And those, along with video analyses from either proof-of-life videos or previous year's competition videos that are available on YouTube, allow us to really get a good idea for what we are dealing with. We identify most likely that these other teams are either going to keep the same design if it proved to be semi-successful for them, or they are going to scrap it altogether. More likely, they're going to improve on a previous design. By doing so, we know how the previous design scored, so we set that as a bare minimum for what these other teams are going to do. From there on, we assume that they are going to make improvements on the previous designs. So, as we set our target specifications, which are shown on the right over there, are our actual target goals for each mining element category. You'll see it's both qualitative and quantitative in that you can see the scores. These scores are set out by us doing these analyses, sort of going through our design process and setting out targets for ourselves. We know we were able to set up the qualitative part of it by examining the rules and rubrics document through which all these are available. And these qualitative analyses are basically a rank set up by the team that allow us to quickly make snap decisions. And we're not going to say snap decisions, really, that's a poor way to phrase it. It's better to quickly qualitatively analyze what we are dealing with. So if you look there, we don't hit our safety inspection, mission failure. If we don't mine a kilogram of gravel, then mission failed again. Now, this is where things get weird for us. Autonomy is third, and while I'm guessing most teams don't necessarily prioritize autonomy third because historically most teams are not successful in autonomy. So we see that as an opportunity to gain an edge on the competition. Not to mention that the autonomy portion is incredibly important, I think we can all agree. From there on out, there are other important elements. Obviously, the mass and the energy consumption will factor heavily into our optimization as we speak on later, along with the other elements, but we attribute less effort to those because we are confident in our ability to minimize those other elements. And what you have here is the hard requirements for us. These are, again, very similar to the safety inspection and the 1 kilogram of gravel mine. These must happen for us to be any sort of successful, otherwise it is, again, mission failed.
So our team is composed of 7 undergraduate students. With such a small team, each team member is wearing multiple hats. We broke down our team into 3 functional groups, and team members are part of one or more of those functional groups. The functional groups have functional leads that manage the tasks of the group and report to the project lead, who delegates tasks, manages overhead tasks, budgeting, scheduling, and overall deliverables for the competition. In order to manage this, we developed a living schedule in Microsoft Project that allowed us to track our tasks and manage our critical path. On top of that, we developed risk matrices and FMEA analysis to predict any risks that were possible for the project or the design and build, and we tried to mitigate them as best we can.
As Dean mentioned, we decided to emphasize certain parts of our robot to improve its quality over previous competitors. Namely, we wanted to increase our digging score, as we felt that was the best way to place. We wanted to minimize our mass, and we wanted to minimize the energy consumed. In order to do this, we looked, as Dean said, at previous competition data and digging mechanisms and locomotion mechanisms to see where there was room for improvement. We also took an approach to use a modular design, aka using mostly extruded aluminum components, so that future teams, should they choose to take up the mantle of our project, would be able to to either benefit directly from our design by improving on it as is, or hot swapping different locomotion or digging mechanisms.
So in order to manage our design process, we took our technical specifications and requirements, and we created design budgets and weighted design matrices. Our design budgets allocated the resources we had for our robot, such as mass, energy consumption, and bandwidth, and doled them out to the different subsystems making up the overall subsystem. That informed our design and helped with our selection. Throughout our selection process, we used our weighted design matrices to score different concepts to pick the best concept. Sometimes this meant going back to the drawing board and reevaluating when we encountered issues with certain designs. We focus on manufacturability and reliability. It's very easy to design something that looks great on a chalkboard, but when you go to build the thing, it's impossible. Our major area where we tried to innovate was through weight reduction and efficiency. By being one of the lightest competitors, we stood to gain the highest score, same as with autonomy and with digging.
So now to make sure you're still listening, I'm going to start from the bottom and go up. What you see on the bottom there is how we handle our component selection. That was specifically using weighted design matrices, pew charts, and again, the past performance data of the previous competitors. That was mainly done through looking at trade-offs. We did several different materials throughout this entire project. You can see carbon fiber on the robot. You can see 80-20 aluminum. In other forms, we did on the electrical side. As opposed to using brushless motors, we opted to use brushless DC motors for our digging, dumping, and our locomotion mechanisms. Now looking at the top, what's going on there is how we really tested the functionality of our robot. We constructed a test pit that allowed us to, it was be more or less full size, but it did not end up working out the way we thought. As you can see by the image in the top right, it is outdoors. Milwaukee weather is not as friendly this time of year as we would have hoped, so we actually ended up having to scrap that test pit and build a much, much smaller one inside that is not shown here. Regardless, it allowed us to test our various subsystems of our robot. That include the locomotion mechanism, which uses tracks as treads, as can be seen there, which again was meant to improve our reliability, as Matt expounded on earlier. And again, it allowed us to really evaluate our target specifications as we built the robot and really see if we were close to meeting our goals.
So in order to build such a complicated robot, design such a complicated robot, the entire system was broken down into 3 primary subsystems: locomotion, digging, and dumping. From there, each system was broken down into the mechanical components and the electrical components, with decisions on the mechanical side informing electricals. These parts were weighed against each other using the scoring matrices mentioned earlier, and as teams came to more realized concepts, they would meet with the other teams for feedback and input to make sure that all of the concepts across the 3 groups had a possibility of meshing with each other. Here's our final robot. As you can see here, it's fairly close to the one on screen. Our final weight estimate, while there is approximately 42 kilograms, our final robot with all of the electronics installed weighs near to 46 kilograms. As we are a first-year team, we don't have anything to go off of for prior experience. So in order to establish a baseline for innovation, we had to turn to past competition data. One of the biggest things we noticed across the board is weight. A lot of teams were using aluminum and steel, which both have excellent strength characteristics, but are on the heavier side. We decided to invest in carbon fiber where we could, which has a far superior strength-weight ratio over any other material we could possibly get our hands on. There additionally is titanium rods supporting certain parts of the robot where we could have used steel, further cutting down on the overall weight. Another common thing that is done is 3D printing. A lot of teams have used 3D printing components on their robot before. We also use 3D printing as it is cheap, cost-effective, and allows us to create parts that we otherwise couldn't due to machine constraints. Where we stray differently is we invested in a PLA that has a carbon fiber inlay, as well as post-processing our 3D printed parts with an epoxy coating. which increased the durability, the toughness, and the tensile strength of our printed parts. And it allows us to replace parts as they break, should they break.
What we have on the screen now is our project schedule. Like we've mentioned, we've had some setbacks and some changes throughout the life of our project, and we used our Microsoft project schedule to track those changes and track our task progress to make sure that we didn't fall behind despite these disruptions. As you can see, our project schedule was mainly unaffected until right around the critical design review. After that, as you can see, we had a major shift from pre-full assembly testing to post-full assembly testing. And that was due in large part to the cancellation of the on-site mining portion of the competition. With that canceled and the scoring changing for the different components of the competition, we focused on design, systems engineering writing, and our outreach efforts in order to maximize our score for the competition, which was our ultimate goal. To compensate for this, we moved assembly along and added more post-assembly testing, which hopefully will allow our autonomy to function just as well as it normally would have. To manage our risks, we developed our project risk matrices and our design risk matrices. Funny enough, in our project risk matrices, we accounted for the government shutdown and the possible cancellation of the competition. Also, in our risk matrices, we noted that there wasn't much we could do to stop that or mitigate it, but our plan was to go on regardless with our build that you see before us. As we were managing our risks for both the project and the design, we had weekly meetings with our advisor, Dr. Philip Vogelweed, where he was constantly checking us on our work, asking us questions, and helping us think of things both from a design and a project management level that we might not otherwise have thought of. Our risk matrices were updated at each of our major milestones, from our preliminary design review to our critical design review, and our budget had plenty of margin in it to account for any major changes in the project or emergency expenses that would come up. So this is our final design. As a first-year team in the competition, we're proud of the work we put in. We've burned the midnight oil plenty of times on this project, and we put our blood, sweat, and tears into it. We've developed a functional design from start to finish, and with our modular approach, our hope is that Marquette University will take this project forward with future teams who can swap in and out and improve upon this as they see fit. We thank you for your time and listening to us, and now we'll show you our robot in action.
All right, at this time, the robot will be controlled from off-screen, so don't be surprised when things start moving. We are fully aware. We are all maintaining our safety plan at this time. Zach, are you ready to move the robots?
I'm ready.
All right. All clear. I would like to see drive forward, please.
3, 2, 1.
Go ahead and stop. Please bring the robot backwards.
3, 2, 1.
Stop. Please demonstrate turning.
I'll be turning right.
Thank you.
3, 2, 1. And I'll be turning left in 3, 2, 1.
You go ahead and spin the digging mechanism, please.
Digging mechanism. 3, 2, 1.
Can you please spin the digging mechanism? Dumping mechanism, excuse me.
Dumping mechanism. In 3, 2, 1.
Thank you. Can you please demonstrate the pitch actuators that move the digging mechanism?
Yes. 3, 2, 1.
And stop. Thank you. We cannot go any further because, again, this is meant to be on the regolith, so we can't actually dig into concrete, unfortunately. Can you do the same with the height actuators, please?
Yes, height actuator. 3, 2, 1.
All right, stop. Bring it back. Thank you. So that's the gist of the general operation. In the actual competition space, in the test arena, we would begin in the starting area again in random orientation with our arrow pointed in whatever direction that may be, whatever our forward direction is. And at that time, in our autonomous operation mode, we would spin 360 degrees as our camera would identify a basically a QR code that is on our dumping bin. That will allow us from there to see the depth from the image and allow us to triangulate our position in the test arena. From there, we will then know the predefined arena space, and also using vision, we will actually traverse through the obstacle area where we will see again our obstacles, and I will make our navigation node in our robotic operating system will allow us to create a path that allows us to avoid the obstacles. At that point in time, we will end up in the digging area where we will begin to dig, obviously excavate the material into the hopper, and we will then return to the dumping area again, traversing through the obstacle area and lining up with the dumping mechanism and dumping the rhyolite. We can do so as many times as possible in the competition space. Again, I'd like to thank you for your time. Anybody else have anything else to say?
We look forward to hearing your feedback on our project. Thank you.
Thank you.
Thank you.